Pulmonary emboli have a profound effect on gas exchange. Obstruction of flow to the lungs increases dead space, so there is ventilation without perfusion. If minute ventilation doesn't change, that is, if there's a paralyzed patient under general anesthesia, there will be a decrease in end-tidal CO2 and an increase in PaCO2. If minute ventilation increases, there will probably still be a decrease in end-tidal CO2, but there could be either a decrease or increase in PaCO2, decrease caused by hyperventilation. End-tidal CO2 decreases to a degree that's proportionate to the extent of the dead space. We can look here at normal blood flow to the lungs. We have the alveolar ducts and alveolar sacs here. We have capillaries coming in that interface with the alveoli. And normally we have a PaCO2 of about 47, which moves into the lung with a pressure of about 40 millimeters of mercury. And in this situation, our end-tidal CO2 would be about 40 millimeters of mercury. And then we have an example of a pulmonary embolism in the same kind of situation, where we have capillaries coming in, but now we have a big blood clot here. So everything is backing up. We have CO2 climbing here because it can't be released. There's no CO2 being released to the alveoli. From the other side, we still have normal release of CO2, and our end-tidal CO2, in theory, could be 20 millimeters of mercury.